Okay, so hi everybody. So I'll try to survey some parts of metric embeddings. It's a big field, kind of, so I'll not go over all of it, but I'll try to go over some. This is a workshop, so the goal is for everybody to understand. So stop me and ask questions. Let's try to make it interactive. So metric embedding is basically some embedding from one metric space into another. Like here we embed some complicated graph, Euclidean space, and we want to preserve some properties. So you can preserve many properties. One of them will be distances, but other like cuts, flows, commute time, effective resistance, other clustering statistics, and whatever you want. And today we'll focus on distances. So we say that embedding F at distortion T, if you preserve the pairless distances of every 2 points up to a factor of T. So no distance is decreased and increasing by at most a factor of T. This is the most basic definition. And it's highly desirable so that the target space will be simple. And the idea is that once you have such embedding to preserve the properties of the original metric space into a simple target space, you can solve whatever hard problem you have in the simple target space and then pull the solution back. So basically, we have two properties: the simplicity of the target space and the distortion. The goals here. And the most classic example of such a result is by Bourgain, who showed that every metric space is embeddable, every endpoint metric space, so everything here will be discrete today, with endpoints. Any endpoint metric space could be embedded into Euclidean space with logarithmic distortion. And that's what this is like, because now whatever complicated and crazy metric space you have, you can assume it lives in Euclidean space, which we all like to work on, and you're only paying for that log n. Maybe it's too much, but this is the best you can do. And this has many different applications. I'm not going this talk into actually all in applications, but one famous one is sparse cut and some others. If, for example, your metric space is the short stack metric of planar graph, then you can do better. As Raul showed, then instead of paying log n, you can pay only squared log n. So sometimes, like some structure in the metric space can help you to get better metric embeddings. And this is tight in the case of L2, as shown by Newman Rabinovich. However, for L1, this is the best that we know how to do. Well, one of the main open questions in the field is to get better, or if you embed it to L1. And the Gupta, Newman, Rabinovich, and Sinclair generous conjecture says that for L1, you can embed always every KR minus graph with constant distortion. It was open for quite a while.
But what could say is dependent on it? It's op distance or
No, it's a short span distance.
And what is not with every edge is going one or
No, you can put arbitrary.
arbitrary.
Yeah, but it's not really. I mean, if you have polynomial ways, then you can just subdivide. It's the same question because you assume constant here, so actually you can assume unweighted if you like. It's the same question. Okay, here another Hall of Famer, Johnson and Strauss. So here you have some high-dimensional Euclidean space. Here I have only 3 dimensions, but things like log n dimension, something really large. And they show that you always can reduce the dimension into log n over epsilon squared, and always paying for this 1 plus epsilon. So this is nice because now like the highest dimension you can think about in Euclidean space is log n. Nothing higher than that is really necessary if you're willing to pay 1 plus epsilon. This is also tight, as was shown recently. It's not that recently now, 8 years ago, by Green Larson and Joy Nelson. Yeah, this also used whatever to speed up computations. You all your clustering, your neighbor search algorithms all go through JL. So this was kind of crush introduction to metric embeddings. However, it's kind of impossible to survey everything. And today we'll focus on three embeddings and some of their spin-offs, which is the title of the talk.
So may I ask something?
Sure.
So this Johnson, Leith, and Strauss. So the original proof of this is randomized.
Right.
You take a random projection. So it is known how to do it deterministically, particular, is it known how to do it in linear time?
So in linear time, we do know how to do it. You basically just sample the metrics of n columns and log n rows, and you multiply every vector with this thing. Because it's very efficient, and you have to think even more efficient using some sparse matrices. However, about deterministic, I'm not sure I don't know this result, but I think.
I mean, deterministic should come with linear, right? Because deterministic, quadratic.
No, you can do deterministically very efficiently embedded. If you want to verify that you actually get it, I'm not sure if you can do it fast. But I just don't know. Yeah, so a very simple. So as I said, we really like simple target spaces, and what we show until now it's high-dimensional Hillian space, which is not very easy. And one very simple and desirable target space is tree metric. So many NP-hard problems become easy on tree metrics. You can do dynamic algorithms, and we all like trees. Unfortunately, trees are not very representative. And specifically, you look on the cycle graph. If you want to embed this thing into a tree, you will suffer distortion log n, linear distortion. So if you delete one edge, the two vertices over the edge you delete it will suffer distortion n. However, even if you allow standard points and embed it to some other tree, it's still known that you cannot do better than some constants times n. So this looks like to be the end of the story. However, this was observed by Karp, I think, many years ago. If you delete a random edge, what will happen? So consider a pair of neighbor vertices vi and vi plus 1, like these two, and suppose that we delete a random edge. So if we delete this edge between them, then the distortion is horrible. You need to go this entire path, so you're paying n minus 1. However, if you delete any other edge, then it's great. The distortion is just 1, pay nothing. And you can see that the expectation, you're paying only 2. So if you're happy with expected distortion, instead distortion 2 is enough. And this is not special about a pair of neighboring vertices. Using linearity of expectation and triangle inequality, you can show that for arbitrary pair vi vj, just break it into all the consecutive pairs, sample random edge, and the expected distortion will be again only 2. So this is nice. We get instead of n into 2 by just sampling a random edge to it. And this is not something unique for the cycle, as was shown by Kashiropoulos, Rao, Talwar, including some previous works by Bartal. This is actually true for any metric space by replacing 2 with log n. So specifically, the theorem, which is, I guess, the key one for today's survey, is that for any endpoint metric space or a weighted graph, you can embed them into a distribution over dominating trees with expected distortion log n. So let's break this theorem. So there are a couple of hard things. So first of all, distribution. So you have, you say, your weighted graph or geometric space, and you can embed the distribution such that every many trees over your metric space. And they're all dominating in the sense that in every tree, the distance between any pair of points will be at least as large as the original metric distance. So nothing is allowed to shrink. And the final one, the expected distortion, will be at most log n times the original distance. So for example, this pair here have very small distortion. Here is like fine. Here is terrible. And the guarantee that in expectation, it always be at most log n. Yes, so we saw in the tree, we have like expected distortion 2, and the distribution was like over n paths, which we can get by deleting one edge. And in expectation was 2, and here we have something similar, but it's log n. And this is also known to be tight. It was actually known even before proved by Aloy et al. And this is tight already actually on the grid. So even if you start with fairly basic metric space like the grid graph, you still cannot improve over this log n. Okay, and this is a very useful hammer again because trees are so basic and useful. You can just, if expectation is good enough, you just embed it to a tree, and from there the life sometimes become easy, sometimes become feel hard, but much easier than general graphs or metrics. And this has lots of applications, approximation algorithms, online, and much more. So the plan for today is kind of as follows. Yeah, sure.
How large is that,
The support?
that distribution?
This is a good question. So the support cannot be small. So think, for example, in the cycle, you cannot do better than n, or some linear, because somebody will suffer linear distortion. So better the support should be at this linear size. And again, I think we can get n log n using multiple weights or something. Other questions? Yeah, so the plan will be to go over the classics first. So we'll see non-optimum embedding with distortion log squared by Bertal, and it will go over pi decompositions, which is one of the key tools of this entire area. And I'll show you this one because it's very basic and simple, and also it was used, the same ideas was used over and over again in many different frameworks and ideas. So then we'll go over some of the spin-offs of this of the basic idea of Bertal online, and then we go over spelling trees. And finally, I mentioned some more recent work on line-free graphs and their embeddings. Okay, so let's start with the classics. The classic embedding by Bertal, the first one which you get polynomial distortion was with distortion log squared. It's based on stochastic partitions of the metric spaces. So specifically, it's the following creature. So I give you some metric space X or weighted graph G, if you prefer, and I want distribution over partitions of the metric space such that nearby points will be likely to be clustered together. So this is called beta delta pi decomposition. Some people call it LDD, low diameter decompositions, and it has two guarantees. So the first guarantee is that every cluster in any of the partitions has diameter at most delta. Well, the second guarantee is that small balls are likely to be clustered together. So specifically, for every small gamma and every center z, the probability that the ball of radius gamma delta, so delta is the maximum diameter we allow. So if you look on the ball of radius gamma delta, the probability that it's clustered together, it's contained in single cluster, so here it's clustered together, here it's cut, here it's clustered together, is proportional to the radius. So specifically, it should be e to the minus beta gamma, or in other words, the probability that you cut the ball is about beta times gamma. So delta is not really important, just a scale, but if you look on the ball of radius gamma, you should think about being some small number. It's the probability you cut is beta times this radius of your ball. And as your ball becomes larger, then the probability becomes larger as well. And as you got gamma will become tiny, and the probability will goes to 0 to cut the ball, or 1 to be clustered together. Yeah, and we say that the metric space meets a beta pi decomposition scheme if you can construct such a partition for every scale delta. For example, you can know that the probability that the ball with radius delta over beta is clustered together is constant. And this beta is called Paddick parameter.
As it for the definition for the beta is fixed, so you say beta composition.
Right, so beta is fixed.
And then it has to work with that.
Right, if you want it to be Paddick decomposition scheme. So usually delta is not important, and beta is the important thing. It's called Paddick parameter. And different metric spaces have different Paddick parameters. And as your metric space has smaller Paddick parameters, it's kind of easier to work with, and you can decompose it in a better way. So we know that by Bertal that every metric space meets a log n Paddick decomposition scheme, which means the Paddick parameter for every metric space, the best we know is log n. And there are some metric spaces with betting Paddick parameters. For example, Euclidean space of the nation D will have Paddick parameter D. And this is tight. By, for example, expander, you cannot do better. Or high dimensional space as well. Okay, so let's go over this construction, how you construct such a decomposition. So this is almost the original one by Bertal, and the algorithm is very simple. So you have some arbitrary order over your metric points, x1 to xn, and for every point by order, you sample some radius. So this is the first point, and I sample some radius, Ri, using exponential distribution with mean 1. And then we just scale it to the parameter we want. So here, suppose you want maximum diameter delta, so we'll scale it by delta over log n. And then all these points join the cluster centered at x1. And then we take the second point, and we sample new radius. And the new cluster will be all the points at distance most r2 from x2, which shall not relate cluster. And then the third point, the third radius, this point could be already clustered, that doesn't matter. Take a third point, grow a random cluster around it, and cluster all the points which are not already clustered, and so on and so forth until everything is clustered. So this is very basic and simple composition. So optimal. So you can see that with high probability, all the radius that we sampled are at most log n. And therefore, the maximum possible diameter after scaling will be delta. So the maximum radius is half delta, and the maximum diameter is delta. So with high probability, we have this probability. And let's say that indeed every ball is clustered into a single cluster with the right probability. So consider some ball of radius gamma delta around Z. So some ball now consider the first time when some vertex in this ball is being clustered. So think of this sampling here, maybe instead of exponential distribution, think of geometric distribution. So you toss some coins, and you continue tossing coins until the first time when you will see head. And at this point, you stop tossing coins, and this is the end of the cluster. So you kind of tell it, so now I see tails, so I continue clustering, and now the first time I cluster some point. So at this point, it's kind of will be decided. If the ball will continue to grow and cluster the entire ball, then the entire ball will go to a single cluster. Well, if I stop in the middle, then the ball is cut. So now what's the probability that I will continue to grow the ball until everything is clustered? So now we use this defined exponential distribution memoryless. So given the fact that you already grow until this, you only need to grow additional, the diameter of this ball, which is 2 gamma delta size to cluster the entire thing, right? And memoryless, so this is the entire probability by memoryless, and because of this exponential distribution, the probability that this event will occur is like e to the minus gamma times the scaling here, which is log n. So you see that we get exactly here the Paddick parameter that promised, which is log n. Okay, so this is the basic tool that we'll use, and we'll see later in this talk another way to construct them. Yeah.
So could this work with a single random radius? So the same radius for all of them?
So yeah, this could work if you, instead of sampling radiuses for every one of them, you can sample one for all and then take a random permutation. This will give you the same Paddick parameter. Other questions? And now let's see how you can use this basic decomposition to construct geometric embedding in trees. So for simplicity, we'll assume that all the edge weight, so we take some, so all the distances are between 1 and then to the 10 or something, some polynomial aspect ratio or spread. If it's not the case, we know how to handle it, but it will be easier here. So now for every possible scale between 1 and phi, the maximum distance, we sample a Paddick decomposition, we scale to the di, and Paddick parameter log n. You know how to do. And now, so we get like log aspect ratio, log phi, different partitions. And now we want them to be laminar, or hierarchical. So we kind of force them to be together. So we say that x and y will be clustered together in the partition of scale I, if they're being clustered together in on the partition I plus 1 until the end. Right, so this basically gives similar partition, but now it's laminar. So laminar partition means that you have your points here, and this is the minimum scale, larger, and so on. And they all, it's like hierarchical, they all refine each other. Okay, and now we put simply a tree structure which will respect this. So this is like maybe like quad tree in geometric space. Now we put this tree on top on this partition. So what I mean by that, so for the minimum scale, pick some representative, add edges to the representative.
So one question. So in the previous scheme of Bartal, you mentioned that it may happen that we sample the next point which is already in some cluster, right?
Right. No, so you take some arbitrary order,
Right.
and we don't care about what happened to the set, we just continue somewhere.
But then in the laminar case, how, I mean, if you sample the next point which is already clustered, then you break the laminar.
No, so think that they take some, establish some partitions, they don't respect each other at all. And then they force them to be laminar. How do they do that? They say that 2 points are clustered together in scale I, if they've been clustered together in all the scales above I. So I can force it to be laminar. I'm losing something in the Paddock parameter because now you have slightly higher probability to cut, but this is not significant. And you will see it eventually in the computation. It's quite negligible because it's like geometric scheme, so
Right.
cancels out. Okay, so now I look on the minimum scale, pick representative and add edges to the representative. And now I go to the scale above, again, pick representative, and add edges from the representative to all the representatives of the previous scale. Now I do it again for the next scale, pick representative, add edges to the representative, and so on, until you get a tree. So this is a tree. Now I should tell you what weights you should put on the edges, but nothing smart about that. Just put if like it's an edge between representative at scale I-1 to scale I, so they are together in some cluster of diameter 2 to the I, you'll just put the weight B2 to the I. Or you also can put the original weight. Maybe even better. Right, so this is the tree. Clear? So here's first observation. First of all, this thing is dominating, in the sense that no distance could become smaller. Why is that? Because I mean the weights I put were always larger than the actual distance. So there's no way you can do any shortcuts. And the other observation is that if point X and point Y are clustered together at scale I, the distance between them will be at most 2 to the I, up to a constant. And this you can prove by induction. So think that you go to the representative at scale I and then back. So the maximum weight you will see along this path will be at most 2 to the I. You'll see 2 of those, and then you will see 2 weights of 2 to the I-1 and so on. This will overall converge to just some constant times 2 to the I. So let me just tell, I guess, some people here. This is not actual thing Bartal did. He used something called HSTs or rule metrics, but I think this is easier to go over. Yeah, so these are 2 observations that we'll use to see that this thing indeed has small distortion. Yeah, so in particular, suppose that X and Y, let me put this index I, X, Y to be the maximum index such that they are not together. So in particular, this means that they were clustered together in I-1 and they will cluster together in I+1 and I, they belong to different clusters. And in particular, this implied by observation 2, the distance between X and Y is, according to the scale, 2 to the I, XY. And now let's see what's the expected distance between X and Y. So this is bounded by if you go over all possible scales and the probability, so like they will be, the distance between them will be 2 to the I X, XY, which is the scale, the first scale where they are separated. And so here I go over all possible scales and say what's the probability that you're separated at scale I, and if this is the case, your distance will be 2 to the I. So actually it will be enough here to go over just the scale where they are separated, in this sense max instead of sum. It's not a big difference, and it's easier to analyze the sum. We'll go over a sum here. So now this is just, so the distance is bounded by the sum of all the scales. What you will pay to separate in the scale, there's a probability to be separated in this particular scale. So now what's the probability to be separated? So recall, so here it's like, it's not the tilde thing, it's just the actual Paddock decomposition. And we've seen that this Paddock decomposition is basically the probability to be separated is proportional to the distance between you. And we can show that the probability to be separated is basically the distance between 2 points, or if you think we talked about balls, but distance is even easier because X is containing the ball around Y of radius the distance. This is scale, so this is like let's say the distance. Actually, this is not super clear. Let me write it here. So what they proved in the slides was that if you have gamma delta, so this is the distance, and like the scale here is delta, right? And in this case, the probability to be cut is the padding parameter, beta times gamma. Right? So what is gamma here? So here I know this gamma delta is equal to the distance between them. But if I wanted to be, so gamma here will be just the distance scaled by delta. So basically the probability to be cut is the padding parameter. So what's the padding parameter? In general graph, we don't want to prove log n times this gamma, which we just scaled, which is the distance by the geometric parameter. And this is exactly what is written there. So this is the padding parameter, and this is the probability, like this is gamma. So this is the probability to be cut, and this is just take from here. This is the penalty for this. If we cut this, this is here. Great. So now this 2 to the I cancels out, and because we assume phi is polynomial, we get log squared. And this is the theorem, that the original theorem of Mertel, which is the easiest one to generalize in different models, that the expected distortion is just log squared. So this was improved to log n. I will not go over how it was improved because it will take too much time, but let me just scale that the basic idea is to sample the padding composition different scale in some correlated manner. And specifically the one I told you will work when you sample the permutation instead of radius. Yeah.
Did you say that this result of log n is tight already for the Euclidean space?
Right, even for two-dimensional Euclidean space.
Oh, yeah, that's my question. Is it like
Yeah, the grid is already tight for that. So in the last part of the talk, I'll discuss more about exactly this type and how it can be improved. But basically, the entire talk, yeah, be some spin-offs of that. So the first, so in the rest of the talk, I have like 3 parts, which will kind of starting from this idea. We're trying to take it in different directions, and there are a lot more of these types. Yeah.
Can I ask you a question? Can you go back 1 slide? I'm curious, what is the Bata 04?
So
So
Bertal 96 was log square. Day 98 he used similar idea, if you're familiar, to get log n log n, and then Bakashiropa et al. Proved log n,
yes.
and then Bertal show how you can use this kind of which I have it here. So he showed how you can sample with padding parameter this thing, which is kind of local pure distribution, and then the telescope to get the final log n. So it's just he shaved the final log n.
What was the Bata 04? What is
So this is like this come before. He published after them.
not aware.
The same year, but after all. And this is a tough paper to read.
Because I'm not aware of the Bata 04. I'm curious.
You can open it. It has some integrals if you're not there.
Okay. Well,
No, this one is the easiest proof.
Right.
It's scary. Something I can't show, but
but everybody cite FRT. So that's
because they are the first ones. But I mean, I guess Bertal have more credit because he got like the first result, and then he get log n, which is like it's tight. And then he managed to do like the right thing a couple of months later.
Okay.
No, but it might be inspired by them.
Right, so that's accurate. That's that paper.
So the first thing I want to discuss after this is about online metric embeddings. So consider the following thing. You have metric points arriving one after another. And each time you see a metric point, you want to embed it somewhere. So suppose, for example, each time you see a point, you know the distances to all the previous points. So like when I get to the second point, I know the distance to the first one. When I see the I point, I see distances to all the previous points in the sequence. And for each point, I want to embed it somewhere. So maybe you can think that you want to embed it into some vector to be in space. Or if you talk about trees, so you want to define some metric, some distance over all the points that you cannot change after you define it, such that these distances will be tree distances. Yeah, once it's fixed, it's impossible to change. So the goal is to kind of to minimize the distortion in some competitive way, or maybe just to say that whatever you get some worst case possible distortion that you will always be possible to achieve. And the first observation is that this decomposition seen by Bertal is actually online, in the sense that you see a point, you sample a radius, and when the new point arrives, it means cluster determined by the previous samples. So this is basically an online algorithm. And this was observed by Indik, again, Sideropoulos and Zoazis, who showed that actually you can run the same algorithm by Bertal and getting distortion log n log phi, which is the aspect ratio or spread. Yeah, so previously in geometric we know how to remove this log phi, but apparently here in online this is required. It should be there. So if the aspect ratio is huge, then the distortion as well might be very large. And yeah. So this basically understood way back. And the question that remained here that was interesting is what about if you want to embed it into Euclidean space, like Bourgain, we want to embed some vectors. So this result in a sense is, is randomized and it's good against oblivious adversaries. But could you do something in L2? So Indik and Tal in the same paper show that actually you can get if you embed in L2 instead of trees, you can get log n square root log aspect ratio. And the idea is similar. So wait, I have some idea. Okay. Here's the idea. So how do you do that? So in the tree embedding thing that we sample one partition for each scale. And now we connect them in some way into a tree. And the distortion was kind of the first partition we were separated. Now for L2, you basically can do the same thing, but now you don't need to make them laminar in any way. For every partition, you can just use some coordinate. And the distortion basically in this coordinate will be proportional to the padding parameter, the probability that you're getting cut. And then you can do it many, many times. So that instead of expected distortion, you will get high probability. And the square root here comes just because of the definition of L2, with the square root there on the coordinates. So this works and nice. However, the issue here is that this high probability is not good enough for online algorithms. So in online algorithms, you have two types of adversaries usually, one which is oblivious and the adaptive one. The oblivious kind of defines the sequence of points in advance, and then you see the points one after another, and you just need to compose it and say that like in expectation, they're good enough. And for this, it's great. This will work because you can settle how many coordinates you want and then use JL, and you will get this with very high probability. However, if the adversary is adaptive and he sees each point that you embed and might decide on his next point it will give you accordingly, then he might break whatever you do, no matter how many coordinates you use. So this was not good enough against adaptive adversary. And the question that remains was what you can do against adaptive one. And as we showed with Sujo and Chava here, is that actually you can take the same idea and make it deterministic. And so the idea is as follows. Can do something better for doubling, like that. Yeah. So I have some, I guess we'll go back to it later. Let me just go over the basic idea. So suppose that you do the same thing on the set, which is sample. Let's try to do the tree. So we sample a partition for every scale, and we take some, and for every such partition, we have some coordinate, which will, in some smart way, should be described here, represent the distance with respect to this partition. So basically, all the randomness in your embedding comes from the sample value in the by decomposition. And, and using the properties of the Paddy decomposition, you can show that in expectation, and even with high probability, if you take enough coordinates, the expected distortion is log aspect ratio square root times log n. Yeah. So, in particular, another way to think about it is that the input is some radiuses R1, R2, Ri, and so on. And and then given these radiuses, this embedding is just a map from, so you get some point, and you get the radiuses of everybody who sampled before you, and then you get some vector. In the tree, you get some point in the tree, but here, if you use the more sophisticated technique, you get some vector. So you can think of the embedding as being some function from the sample radiuses to a vector. And now you can show that the expected distance given 2 points is just some integral in this over all these radiuses you sample. Here. And the result is like the right distance. So the result here is kind of the correct distance between the points. So this is the vector, and this will be just the this kind of the correct distance up to the distortion. However, you can know that while this thing is random because you need to sample radiuses, once you look at the functions are not random. The functions just, just some creatures living in the function space. And there's nothing random about that. I mean, once you define, just definition of like, you have some distribution of radiuses and given to like 2 points and like, just get to compute this exactly. Nothing random about that. And this is nice because now instead of some random embedding, you have functions, deterministic functions living in the function space. And now like you can compute deterministically this function one after another, and then you get some collection of deterministic functions that have this property that you want. And kind of the distance between 2 functions in the function space equal to the distance between the points that you want to preserve, or the expected vectors. Yes, this should be expected vectors or this distance up to distortion. And this can, and now kind of you just can deterministically in an online fashion compute the function and compute accordingly the vector that will represent it. I mean, given a collection of vectors in L2 or functions, you can just find some way to implement them in L2. Nothing about that. So this is the basic idea I want to cover here. Any questions about that? Okay, so I have some open questions here that I want to post now. Let me just go over some more background here. So, so in this specific result, we have 2 parameters here, like log phi, square root log phi, which is square root of the aspect ratio times the padding parameter. And if you have better padding parameter, you can do better. For example, for doubling metrics, which is some version of what define doubling, but some generalization of Fourier space, which have better padding parameter, which in particular is possible to do in an online fashion, you can do better result. It's the padding parameter, doubling the dim, times square root log phi. And again, it should be known. And actually, this square root log phi is known to be tight. In particular, we have some, there are some like spaces which have constant doubling dimension, and even series parallel, which is a subfamily of planar, when we have this lower bound of square root log phi. And instead, you also can say, let's suppose that I don't want my result to be dependent on the aspect ratio. What can you get? Just on n. So the best you can hope for to get here is square root n. Or if it's geometric space, yeah, there's the tilde. For doubling, don't even need that. And this is tight as well. However, let's go back over this result that we just discussed. So the caveat in this entire result of the deterministic embedding is that the dimension is huge. If you just do the thing that I described, that each time you do some ground sheet or whatever, and eventually you'll get some vectors. But the vectors will be of very high dimension, basically linear dimension. And note that you cannot use JL here, because the entire point was to cope against adaptive adversary. JL will not work against that. So yeah. So the one question is, suppose that I want small dimension. What can you do? So we know, okay, using linear dimension, you can do this. But if I want, like, say, suppose I want only to use D coordinates, what is the best distortion which is always possible to achieve? So yeah, so we using even let's ignore the aspect ratio for simplicity. So in general, you can always get square root n using linear dimension. And Human and Rabinovich studied the embedding into a single line. And here they showed that you always can get exponential distortion, and it's indeed required. So for the line, we also kind of understand the question. For unbounded dimension, we understand the question. But in everything in between, it's completely open. So in particular, even for dimension 2, we don't know if the answer is linear, like polynomial or exponential.
So this is connected to Sergio's earlier question, right? If we have a deterministic version of JL and then.
Yeah, but I guess if you have the deterministic version of JL, it probably will be take all the points into account. I mean, you definitely don't have all the deterministic version of JL.
If something is like unclear, then you said you have linear dimension from the top. Zero.
Right.
Then later you said square root n upper bound is linear.
This is distortion.
Oh,
This is distortion, the dimension is linear.
okay, but then the top also use linear dimension.
Right, this is the same result. I mean, this is just, just I want to kind of ignore the aspect ratio to like may have one parameter. So this is the same result.
So your aspect ratio can be large. Then.
So if the aspect ratio is larger than exponential, then it's not, I mean, it's kind of, exponential is the worst case. If it's larger, you can do square root. The derivation here. Yeah, the question I want to ask is about, say, dimension 2. What's the right answer is? Polynomial or exponential? Yeah, actually, and actually, I have another question about also about online embeddings. I guess well, this one might be. I'm not sure if it's very hard or not. It might be not very hard. This one I really don't have any idea how to approach, but let me tell you about anyhow. So we show this definition of pi decomposition, and we saw that there's like Bartal showed us that any endpoint metric space has pi parameter log n. This is tight. This could be also done in online fashion. However, suppose so this could be in online fashion. And if we have more basic metric spaces, we can have better padding parameter. And one famous example is, say, planar graph. So here, Klein, Polk, and Rao showed a long time ago that 30 years ago, basically that the shortest path metric of every planar graph have padding parameter just a constant. And we have now like since then about other algorithms. I understand this very well. However, what if you get the points in an online fashion? Specifically, suppose you get the same kind of framework that I had before. You have points one by one. For each point, you get all the distances to the previous points. And I promise you that this metric that I show you, all the distances coming from a shortest path metric of a planar graph. So now I know that this metric admits constant padding parameter, but I don't tell you what the planar graph is. Is there any way to get better, get some constant padding parameter in an online fashion? And if you get this, then it's like, no, we know the result we had before. You could replace the log n by the padding parameter that you will get. So like, let me just be clear here. So this is the shortest path of a planar graph. And you don't know what the planar graph is, and now you get the first point, and now you get the second point, the distance here is 3. I tell you distance is 3. Now, distance, the third point, distance to the first point is 3, to the second point is 2, and so on and so forth. So I give you points one by another, and once you give a point, you need to decide to which cluster it goes. And once you decide, you are not allowed to change your mind. And the question is if there's any way to sample such a partition in an online fashion. Get something better than log n.
You guess, and then just use that one.
Using the padding parameter.
You just change the.
No, I tell you the padding parameter is constant. I know it. It's planar graph. but I don't know how to sample them because I mean, all these algorithms, KPR and everything that comes after, uses the structure of the graph. So here you don't have the structure of the graph, you just have the promise that it is coming from planar space, a planar graph. Yeah. So for trees, after some thought, we managed to do something slightly weaker. So here I want to cover balls. For trees, we managed to do that given 2 points, I can like they cluster together with some closure probability, but it's not goes to 0 as they come closer. It's like a fixed threshold. This version we managed to do for trees, but that's that. But I mean, this basically is not sure if it will be good enough for the embedding, but something. Okay. This was for my open questions, and now I want to go over some more. Yeah,
So it makes sense to use the course to change the tree, constant amount of change.
different question. It might be interesting as well, but yeah. But you need to do in some like if you yes. So the record is how many times you change the point, the cluster of a point. Yeah, it might be interesting. It could not be used for the embeddings that we have, but maybe from some other type of embeddings which are all recurse as well. What do you mean offline setting? If I give you all the points in advance, even if you don't own in the graph, you can just cook up some graph that maybe will not be your graph, but it will be planar. Right. This if I don't have time. If I have time, I'm not sure.
Question for the earlier outline algorithm, what is allowed deletion from insertion and deletion?
So I mean, we don't know how to use that. Well, it's not a problem. It's just the scale will be according to the number of points you saw. If you want it like to be, you know, some sliding window or something that the distortion will be proportional to the points you see until now, the active points. Then if you don't allow me to change anything, I don't need to help. But if you will also record it, perhaps.
So I think for obvious adversary, for age insertion and deletion, there is one result that you can make for one. But
For dynamic.
for dynamic,
Right.
but for ages, not for.
Okay, so any other question of that, or we move to the next part of the talk? Okay, so now we forget about online and move to spanning trees. So a lot of people here work on graphs, and everything that I defined till now was some abstract trees, abstract metric spaces. So it was not spanning trees. So suppose that your metric space is like shortest path metric of a graph, and you want to sample a spanning tree. For example, if you want to use it for routing or something, you actually need to be a spanning tree, not some abstract tree in the sky. So what can you do? So yes, so Bartal does not make subgraphs, and also these two does not do subgraphs. However, there'll be a lot of work on that, and the engineers go around with name on improving some previous work of Fanon et al. And is Elkin et al. Basically get almost the optimum thing, which is log n up to log n factor. This log n factor is here for some long time now, and one question is to remove this log n factor. However, it's not a good idea to approach this in this workshop. It's been there for a while. However, yeah, what I want to show you is something which I saw like this 2 months ago. It's been there for a while. Which is a different algorithm to construct. It's not optimal, getting distortion no Q, but it's super elegant, and it's using this hammer that we were using for the last decade a lot, NPX, which I always want to present as well because it's survey of metric embeddings. It was very useful for us for everything related to graphs, basically. So I'll start by going over this neural penny tube, which is another quality proposition, very different from Bertal. Getting the same log n factor, which is optimum, but it's the right thing to use if you work on graphs. And then we'll see how to use this kind of graph type of decomposition to get embedding into spanning trees. So this works as follows. So you have your graph, and you have the centers. So in the actual algorithm, everybody's centered. Let's think that you have some small number of centers, and each center will have some wake-up time. So this center 1 has wake-up time 4, this one have 2, 4, and 1. And think of this like you have some time scales which go from negative numbers to positives. And for every vertex, for every center, sorry, once the time arrived, like minus the wake-up time, he wakes up and he starts to create himself a cluster in some Dijkstra manner. So first of all, he clustered himself. So these two centers are now clustered, and these two are still sleeping. And now in this next second time step, they all cluster all their neighbors. Well, these two are still sleeping. And now in the next time, so they cluster all their neighbors. Well, this now time is wake up because time 2, and this is still sleeping. And then next time step, they cluster all their neighbors. This wakes up. Then they continue where in each time step, everybody clustered their neighbors until everything is clustered. And this is the partition. So formally, this is kind of my story. Formally is the following. So for every center, you have some shift, which you call delta t. This was the wake up time. And each vertex v goes to the center that maximizes the wake up time minus the distance of the center. So suppose that everybody wakes up in the same time 0. Then what we get here is just the Voronoi partition of the graph with respect to the centers. However, what we did here with the immigrant Alvin is they introduced some noise to the Voronoi partition. And now, like, if it's just the Voronoi partition, this is the mystic thing. And maybe the area here get broken to many, many clusters. So this is that. While once you introduce some noise, then this is like similar to Voronoi partition, but now you break all the sharp borders of your clusters, and you manage to prove that this thing is a decomposition. Right. So the way to think about it is that you have some race between the different centers, right? So like in this definition, this is like the race, and from my perspective, so this like I'm looking from the perspective of a single vertex v, and it has and like I'll go to the first center, the max center that maximizes this thing, which is the wake up time or shift minus distance. So it's kind of a race, but it's not really like an Olympic race. There's a couple of differences. So the first difference is unfair race, right? So each participant in the race, each center has a different starting point, which is accordingly this distance to the vertex. So when I say closer to the vertex, I kind of start like in a better position and have higher probability to cluster it. And the second difference is this is not a race on like there's no distance that you should go upon that the first one who goes beyond distance is the winner, but it's a race of endurance, right? So like they have this parameter here, delta t, and you can think that kind of again. So we'll sample these parameters using exponential distribution. So you can think that like they run and sometimes they just drop tired and stop running. And they like this to continue running, and they continue tossing coins. So this is the differential distribution, and this is nevertheless, which means that the runners, they just drop tired at some point. It's not that they become more and more tired, like horses. They don't know where to stop. Right? Yeah. So this is kind of the race. This is the way I like to think about MPX. Yeah.
Is it the same as the weighted runway? The random weights?
So there are some, I'm not sure exactly what you mean. There are some versions of Voronoi where each center have a different scale, and it's multiplicative. Might be. Yeah, this is like additive noise. Maybe what you mean is multiplicative noise. So multiplicative noise is kind of don't have scale, really. And this is for specific scale. So I want every cluster to be a scale called delta. So the noise here is like additive.
There are also additive Voronoi diagrams. That if additive mix them.
No, but different starting time cannot be captured by the weight, right?
You can run the same thing in Euclidean space, and nothing special on graphs here, other than it's very efficient to run on the graph. But,
The artificially weighted Borromean diagram.
It looks like it, but
Or at least it's not.
it is additively, yeah, the noise is additive. It might be in geometry before NPX. Okay, yeah, so the noise here is, again, as I said, is sampled using exponential distribution with mean delta, which is a scale I want, over log n. So basically, you promise that the maximum, shift or regular time is delta. And theorem, I'm not sure if it's NPX theorems, but their algorithm, that this thing gets padding parameter log n. So let's prove it. It's quite a short, nice proof. So this is the algorithm. You have the shifts, and the vertex v will join the center that maximizes this shift minus distance. So consider this. So like these red points here are the centers, and this center is the distance dt, and this is the ball I care about. The ball of values gamma delta v. Then I am asking what's the probability that this entire ball goes to a single cluster. In the sense that for every vertex in the ball, we have the same winner in the race with different races because they all have different starting points. And yeah, so and the way I like to think about it is like it's a race between these potential centers, and you can think this is like the result of the race. So this is the winner. He ran farthest, and this is the second place. So the second one, according to like if you order all the centers according to this function, this is the first one, second one, and so on. And the key observation is that points in this ball have different trace. How is different? They have different starting point striking. However, because they are so close and they're in the same ball, and the shifts are all the same, so the shifts are global. The races are almost the same. So they can be changed slightly, but not a lot. And specifically, you can say that every ball, every vertex here goes to an almost winner. In the sense that by triangular inequality, the distance between T1 between V and U in the same ball in this function is at most by this parameter here, which is bounded by their distance, or twice the distance, which is 2 gamma delta. In the sense, I know that every point here will go to somebody who maybe not one, every point U, sorry, here, will go to some center which maybe not the winner one, but it could not be very far away. Specifically, the only centers which is possible for a point for a vertex U in this ball to join are called almost winners, which will like get to the distance from them, from their point in the race. The winner is at most 2 gamma delta. And now recall that this thing is memoryless, right? So we can think that, and then we go back to this picture. So we have all the centers, and at some points they're like remaining 2 active centers, T1 and T2. And I don't know which one of them will win. And at some point, one of them kind of drops tired and stops running, and then the second one continues running. And it's memoryless. So if it will continue running for long enough time, then there will be no almost winners other than the winner itself. So specifically, one of the second ones can drop tired, this one continues running, and it's running according to memoryless exponential distribution. And by memoryless comes the probability that it will, if it will run farther away than 2 gamma delta, then there will be no almost winners, there will be only a single winner. And by memoryless, this probability and this distribution we took is just e to the minus this gamma times the parameter of the distribution log n. And if this event would occur, like here, so here, like the one almost winner, here around far away, so there are no almost winners, then everybody in this ball will join a cluster of T1. Therefore, the entire ball is clustered together. So. Now, why do we like this decomposition? So, one reason, I guess, is so you can see that this all the pictures here. this thing is inherently connected. It has what we call strong diameter. So the distance between any 2 points in this decomposition will most delta with respect to their subgraph. And this is useful for all graph applications. Okay. Questions about MPX? Yeah.
So this is guaranteed that you have diameter delta with high probability.
Right.
One worst case, you probably need to do some truncation.
Right.
But I only find puzzling or truncation, like the memory list property. How would you think about this with respect to the
I
truncation?
mean, it's quite technical.
Right?
So you can run truncated exponential distribution. Take example this, assuming the maximum that you get is at most delta,
Right.
and then there's small tail which kind of makes some noise, and then you can take some integrals and sum them all up. You just say that in this case it's like negligible. This is the reason you need the log n basically. This is one way to look at this. You can also say something else. You can say I just run my algorithm, and if somebody went too far, which is highly unlikely, then we'll just redo the entire thing. This also works.
So if you're in the centers, are you actually running it from all the centers or all the vertices of the?
So in general, graphs will run for all the centers. There are some cases when it's better to run from subset of them. Yeah. Mm-hmm. Oh no, the cartoon is mine. It's my daughter. Yeah, I tried AI, but it didn't work. It's not like exactly what I wanted.
Was almost taking the credit.
No, I talked about the eye figures. I understood better the question. No, I'm not able to talk it. It's completely out of my reach. This is why kids okay. So now we'll see a result by Becker et al. It's quite recent result. It was originally in the distributed community. This is the reason I didn't see it until recently. It's super elegant algorithm to get spanning trees. So now the goal is to do the same like Bartal thing, but instead of getting some tree, getting a spanning tree of the graph. So you cannot use some general compositions. We're using so classically people were using something called star decomposition thing. But now we use MPX, which is way more elegant. So now I give you a tree, a graph, and we have some arbitrary center x0. And suppose that the entire graph is at this, like all the points in the graph are a distance r from the center. So this is the radius of the graph with respect to x0 center. And the first step in the algorithm is to sample some radius r0, which will be between half and 2/3 r. And this will be the first cluster. Now comes the second interesting point. So look on all these edges that we cut. So take maybe things continuously or something. Some of the edges like being cut such that one point is inside the wall and the other is outside. And what we'll do now is we'll run MPX with respect to these points. So think maybe of the graph when you remove this entire cluster x0 and you kept only the, maybe you kept these tails here. And now you run MPX from this point. So basically, the exact thing to do is to run MPX, but when the shift of each point is not just random, but you also want to take into account the distance to the center. So this is basically the shift. And you sample it using exponential distribution. So previously we have, so now the scale is R. So we want to get something below R, to get something like half R or whatever. But so we get like R over log n. We also use some epsilon here, which we'll use in this algorithm. Right, so now you just run MPX and you get some partition of all the graph of the vertices out of the wall. And now the algorithm is simply so you can see that maybe before the entire algorithm is this. So we know that with high probability, all the shifts, at least these parts, are at most epsilon r. And right, so we kind of it's like in this the noise in the Voronoi distribution, in this noisy additive Voronoi noise is just epsilon r. So consider some point here, V, and suppose that the shortest path from V to the center, x0, goes through this point y6, x6, and then you go here. But V was clustered to different cluster, to x5. Instead of going to x6, we went to x5. So, so now the shortest path, if you go to x5, might be longer, but not much longer. Because if x5 won v over x6, it means that the maximum advantage that it could get from the noise of the Voronoi is only epsilon r. So if you go to v through x5 instead of x6, you will pay at most, so it will be longer by at most epsilon r factor. This is like the Voronoi and the MPX that tease us once you do this thing. Okay, so this will be important. Right, and because you know that the distance from x0 to v is at least half r, because it's out of the ball, the distortion we get here is only 1 plus 2 epsilon by going to the winner of the MPX. Okay. And now the unfamiliar algorithm. So just recurse on every cluster and connect them all together using these cut edges. This is the algorithm. And you can see it's indeed a spanning tree because the only edges that are is actual edges from the tree, and everything else is recursive. Okay, so the algorithm is clear. Let's see that it has some boundary distortion. The analysis will be very similar to Bertal, basically. So yeah, so consider this point V here. Let's see the first important property. And now in the final tree, I will go from x0 to x5 to v. However, I will not go the shortest path. We'll go using some recursive path that was computed by this tree. And we know that like in the first step, it could increase by 1 perception factor. And if you assume a polynomial aspect ratio, the depth of the algorithm is most log n, we can prove that in each recursive call, you will lose an additional 1 perception factor. So overall, you can prove that eventually the distortion, the distance will be the actual distance times 1 plus epsilon in the power of the depth of the recursion, which we assume is log n. So overall, you get 1 plus epsilon in the power of log n. We want to get, and we want it to be a constant. This is the reason in epsilon, so you just pick epsilon to be some 1 over log n, and you get the constant here. So here's the first observation. The distance between any vertex v in the tree to the center is at most twice the original distance. And this is very useful because it gives us the false observation. So suppose u and v here were separated at this scale r. So the distance in the tree will be, you go to the center, like the maximum, like some bound of the distance. You can go to the center and go back. And in this case, the distance will be from v to the center is twice the distance, like 2r at most. This is also most 2r, so the kind of the distance, if you're separated at scale r, is r, which is the same thing we have in Bertal. Right? So this is nice property. And here's the second property. So we use the MPX. Right? So what the probability that u and v are being separated? So there's some probability that you're being separated by this ball. By this is quite negligible and proportional to the distance between them. And we'll ignore that. But if this doesn't happen, so we just run MPX. And MPX, we know, gives you a pi decomposition. So the probability that this entire ball, well, we care about u and v here, but the MPX promises that the entire ball, when we take gamma to be like distance over r, is in a single cluster, right? With probability, which is like the spanning parameter. So here I have gamma times the padding parameter. And the padding parameter, so basically it's log n, but because I have this epsilon here, so it will be log n over epsilon. And this is the point to recall that we take very small epsilon, and therefore the probability to cut will be instead of log n times the distance over the scale will be log square. Right? So this is what we get for the epsilon. So the probability that they are separated, u and v, this is the wrong direction, is at most log square times distance over r. And these two properties are exactly what we had in Bertal 96. Now we can just plug them in the same computation and get the final result. So basically, we call this computation was the expected distance from x and y. Is you go over all the scales. For every scale, how much you pay. So it's the same thing as we had, R. It's 2 to the I. times the probability that you're being cut. And this was the same thing, but instead of padding parameter log n, we have log square here. And overall, we get a log cube. Good time for questions. Yeah,
They somehow improve the view, assume that the metric is like planar or.
sure. If the metric is planar, I mean,
It seems like this
we're using this technique.
construction of
This
clusters.
is, I think there is some way to improve it, log square even somehow. Not sure how, but the narrative, for example, here is not clear how to use it because NPX is not better on planar graph. At least we don't know how to make it better. But I think definitely like, you
Because it
can.
somehow builds those clusters
Right,
further
but-
further and like in buffered the
Actually, if I recall correctly, there is a result getting exactly log n graphs. I'm not sure. There's been one before FRT. I'm not sure if it was spanning or not. Yeah, so sure correctly, but it might be still log n or log n. Yeah.
It's very nice. It's, yes, common. Sort of actual cover without moving the fast. How fast is the construction? I wonder if you.
No, so this is very fast because NPX is very fast. But NPX is basically just run the extra linear time. Maybe some heat on the side, so log n. Right, there's nothing here. Like you just sample the center, you find the thing, and then you run NPX. This is not a extra with some noise, but it's not taking really time. And then it recurs. So yes, yeah, it will be n for log n. So we get to the final part of the talk. So there will be nothing more technical. I just want to survey some of the recent results we have from structured graphs. There was some advances there. So yeah, so we see in this basic result by T, which get every metric could be made into a graph with a distortion log n. And this is that. So now once you have a tight result, you say, okay, so let's try to move it around. It's like very general. From general metric to trees. Let's suppose my metric is more structured. For example, I have like planar graph or fixed line free graph, tree graph. Could you do better? And as we said, no. So by Lon et al, even the grid log n is that. Okay, so simpler source space doesn't help us. Maybe richer target space will help us. So for example, if instead of embedding it to trees, I want some richer target space. One example could be true. If I want some constant tree with graph, I want to embed my geometric into or the planar graph, and it still fix the planar, it was stopping out, into some constant tree with graphs. Could you do better than log n? And the answer is still no. So for every constant t, there is some planar graph, such that the embedding of this planar graph into this tree with t graphs would still require distortion log n. So this was quite frustrating, and we've been stuck on that for a long time until Fox-Epstein and Klein and Schild were the first one to get a side breakthrough to here, and they proved additive distortion. So all this talk was about multiplicative distortion, but using additive distortion, we can do something. Specifically, they showed that given a planar graph with diameter d and any parameter epsilon, you can embed it into graphs with tree with polynomial 1 over epsilon and additive distortion epsilon delta. So what does it mean? So, and this is deterministic. What does it mean? That you have some diameter d here, and the guarantee is you have some embedding it to some graph with small tree width, polynomial 1 over epsilon, and such that for every 2 points u and v, the distance will be at most dominating, and the distortion will be at most additive by epsilon d. So it will increase by at most epsilon d. So if you started with something, so if you start with some far points, then this is a good distortion. Yeah, this was nice. The next question you should ask, okay, so we understand planar now. What the question you should ask, what minor free? Would you do better for minor free? And that could you do better for minor free? And the answer is still no. So once you go slightly beyond planar to K6 pre graphs, so just take basically grid, put a vertex on top of the grid connected to everything is already too hard. This we cannot do. So basically there is K6 graph such that every classic embedding, so this was deterministic, so we want also deterministic, will require tree width square root n. To get any like meaningful thing. Okay, so one thing is, but what we can do when deterministic doesn't work, when they know answer for that, try stochastic. And stochastically you can do better. So yeah, so we show Cohen Dad, Hung here and Klein using stochastic metric embeddings. You can get anti-distortion expectation mod epsilon d, and the tree width here is, so it's not clearly 1 over epsilon. For 1 over epsilon, you get a log factor, but it's still good enough for polynomial algorithm. Left and so it's open to remove the dependency on n here. This is one open question, I guess, which is good here. But I think even a better open question is, so all these results kind of that we have for minor tree graphs in this type of frameworks go through the structure theorem, which means that it's completely useless for any parametric thing. And it will be nice just, given a slightly better, larger tree width target, but without going to the structure theorem. It will be nice here. Okay, the final things I want to mention in this context is the following. So we know that using on this lower bound, for every fixed tree width, you cannot do better than log n. What if I allow you some large tree width? What if I allow you the tree width to depend on the cardinality of n? So here there was another lower bound, showing that every stochastic embedding of planar graphs even into tree width graphs with constant distortion requires tree widths log n. So basically there was two lower bounds. One saying if you want constant tree width, you have distortion log n, nothing better than trees. If you want constant distortion, you must have at least tree width log n. And so the question really, okay, so if I allow you tree width log n, would you do something? And this was shown quite recently by Cohen, Lee, and the Pilichu brothers here. Yes, you can do better. So for every minor tree graph, you can get expected distortion alpha epsilon. This is nice. This is only good enough for Q pieces. With tree width, which is just a polynomial in log n, like log n times 1 over epsilon, and the structure theorem more constant. But for planar graphs, yeah, they get something. So this is already with Shinchi here and Jonathan as well. You can get log cube, and there's no structure theorem in planar graphs. So you can get like multiple distortion of epsilon and tree width graphs and small tree width, like small poly log, but there's lower bound of log n, and they conjecture that you can get actually log n over epsilon here. There's a polynomial gap here between upper and lower bounds. It's fast, but it's maybe late. So let me just wrap up and say that so tree embeddings being invented 30 years ago, and there was not more. The first polynomial polylogarithmic distortion was 30 years ago, and it has so we saw several spin-offs, but actually there are much more that I was not able to cover. Let me just call some of them by name. So the Raki trees, I think Harold Raki is here in the other workshop, which gives you log n expected congestion. This is good for previous routing. In the sense you sample a tree, and kind of the expected flow over the edge is only log n. Another celebrated result was Ramsey trees. So this means that you want a worst case distortion guarantee, which is impossible to get in trees. What you can get is to say that there's a large subset of size n to the 1 minus 1 over k that has a worst case distortion k. But you don't get to choose a subset, just you know that it exists. Somehow like Ramsey structure. The structure is being a tree. There are also clan embeddings, which is kind of dual of that, which means you can get one embedding with worst case distortion, but it's not a real tree. It's kind of each vertex has many copies. And yeah, you have scaling distortion, which means that you almost that the log n is the really worst case of distortion. You can show that for most of the pairs, for example, half of the pairs suffer only constant distortion. And the amount of pairs who suffer distortion log 1 over epsilon is only epsilon fraction. There being prioritized distortion, which means that you give some priority over your points, and the distortion of the pair I and j is only log I instead of log n. In the sense, the more important points suffer from small distortion. And there been, as Sujay mentioned, dynamic versions when you maintain, you have some graph, when you delete and add edges, and you can maintain embedding into a tree with some logarithmic distortion. And they've been distributed in the congested local model. So this is actually the one we saw using NPX. And there were hop distortion. So suppose that you have a graph and you want to preserve distances, but you only allowed to use h hops. So this is something which originally was very hard to work with, and it was shown that it's possible to embed it in the trees. It will preserve in some like Ramsey action type, that preserve all hop distances. Wait with the picture. And the last one that was really recent in this stock is another very nice spin-off when embedding D graphs into DAGs with a small expect distortion. So this one by Nicole and Seth and Gary. Yeah. So, and I guess there's some more that I didn't mention here. I was trying to recall as much as I can this morning. This is what I came up with, but I guess I missed some. And yeah, I guess that's that. So this one's we covered. This was the pi decomposition, embedding into trees by Vertal. This is the open question about the pi decomposition of plane and graph. This is the NPX, and then embedding into spanning trees. That's that. Thank you. More questions?
More questions over the coffee break?
Just want to make a quick comment. So you said about this enormous dependency on R in the structure theorem.
Right.
So recently there was a paper in structural graph theory community by Max Goelski, Sebastian Widek, and Michał Seveyen, who gave a new proof of the structure theorem giving polynomial bounds.
Oh, really?
So all of those order of R are actually poly R at this point. I'm not entirely sure what are the algorithmic aspects, in what time they can compute this decomposition, but they give a structure theorem with poly R all the parameters.
It's amazing. Thank you.
It's now only 200 pages.
Okay, other comments or questions? Yeah. Mhm. So it was implemented in the distributed fashion. This was the point, I think.
Still, when you do it, still look like the static composition. This is different cat.
It's very similar to static composition. I think it's like nicer. It's nonsense.
Distributed, you mentioned about the results in local and context. Is it also like there are results in NPC?
I'm not sure. I'm not familiar. Okay, thank you.